Of course, Professor Atef is well known, and we don't need to introduce. He is well known all over the group of microwave on the globe. He is a professor in electrical engineering department at Colorado School of Mines. He joined since August 2013. He is also a fellow IEEE life fellow, and he, of course, is the main editor of ACE's journal. And we welcome Dr. Atef to give the speech.
So thank you very much for the introduction, and I really would like to thank everyone, especially those who invited me to come here, Dr. Ismat, Dr. Saeed, Dr. Ahmed Atiyah, Dr. Hadia, Dr. Hala. Oh, okay. So I'm always happy to come here and talk a little bit about what we're doing, and it's always a pleasure to come here and do this. Yeah. Just a brief background about who I am and where I came from. I graduated from Cairo University in 1976, and then another bachelor degree in physics in 1979, and then I spent about 3 years to get my master's degree here in Cairo University. So I finished my master in 1982. I went to Canada to do my PhD. I remember the day, it was about 28th of December 1982. First time in my life to see snow. And I found Dr. Sebak waiting for me in the airport with a leather jacket so I can protect me from the cold. He and I were classmates since undergraduate, and we have long history of friendship as well. So I went to Canada, spent about 5 years doing my PhD, and I was hired later on as a postdoctorate in Canada, but I didn't stay for more than 7 months, and then I went to University of Mississippi, 1987, stayed there until 2013 for about 26 years there, and then I moved to Colorado School of Mines, 2013. This is my 10th years at Colorado School of Mines. So you can imagine that I'm getting old, very old. I'm going to retire maybe a couple of years or so. But well, anyway, that's my history. And the topic I'm going to talk about it here, maybe one of the topics that I personally get involved in terms of very close to microwave rather than antenna engineering. My main research is basically computational electromagnetics, antenna and antenna arrays, and RFID system. But you are going to see that everything we do here is basically relies on the finite difference time domain, which is a technique that we publish on it a lot, papers and books and so on. So the key point is that in the numerical technique, especially finite difference time domain, the way that we are implementing it, we can allow for circuit element to be integrated into the simulation and the solution based on electric and magnetic field based on Maxwell equation. So we can integrate voltage source, current source, resistor, inductor, capacitor, and even a nonlinear element, which is the diode. All these are already been integrated, and you can solve any electromagnetic problem, including all these elements or multiple of them in the same simulation by using updating equation for electric and magnetic field. We also have done some work in terms of including dependent current source and voltage source. And the reason for doing this is that when you have a transistor, for example, and you would like to get the equivalent circuit of it, you are going to see that the equivalent circuit includes dependent sources. So we have done this already, but once you put dependent sources into the electromagnetic simulator, you have all kind of constraints and all kind of conditions to be able to get a stable code and code that works for all applications. So the alternative is that basically, why do we need a transistor there? In many antenna application, many array configuration, we need to combine the power, we need to split it, we need to improve it. So most of the time we are going to use amplifying circuit. amplifying circuit is going to have some transistor that you don't have a linear relationship between the voltage and current between the input and output terminal. So those kind of devices or elements, we call them nonlinear devices or elements, and we need to be able to integrate them into an EM simulator in a much easier way. So this is the whole objective of this talk. Before we do this, for example, when we did the diode implementation into Maxwell equation, that basically the core of a simulator, we looked at the IV characteristic of a diode between the two terminals of the diode, although it is nonlinear, but it's very simple, one equation, and we managed to be able to solve this equation every iteration in the time domain to be able to integrate the diode into the EM simulation. When we have transistors, things like this is not going to be easy. When we have elements that does not have nonlinearity, we can simply represent the element in frequency domain by the S parameter, which all of us know the S parameter, how to handle it, and we can insert the S parameter as a black box into the EM simulator. However, S parameter is not going to allow us to be represented in the EM simulator except at one frequency. You can't have the S parameter. You can have the S parameter for multiple frequency, but for each frequency you are going to have a different values of the S parameter. So the difference between S parameter and X parameter is supposed to allow us to be able to have a black box for nonlinear component, and this black box is going to contain all the effects that are happening due to the nonlinearity of the system in terms of the fundamental frequency and many harmonics as well. So this is the whole objective here, is to be able to take a nonlinear component represented in an X parameter black box and be able to put it into an EM simulator and conduct the simulation. Before we do this, we need to figure out how do I get the X parameter itself for a nonlinear element. And this is another part of the talk. Recently, maybe a couple of years ago, companies started to use network analyzer, special network analyzer, to be able to extract the X parameter for nonlinear component. So that was the only source to be able to get the X parameter values for a nonlinear component. What we have developed here is that we allowed the finite difference time domain technique to be able to extract the X parameter, put it in a black box, and then use it later on for any other simulation. So how do we extract the X parameter? We use our knowledge and the way we make the nonlinear component an equivalent circuit. We use a dependent current source and all other resistive inductor capacitor components, and we simulated using finite difference time domain, extract waves, input and output from this configuration, construct the black box, and then we use the black box into any other simulator later on. So this is a summary of what I'm going to try to do. Unfortunately, I can't explain all this without equations. So there will be some equations. Some of them are going to be simple. Some of them are going to be very complicated. I'm not going to go through every detail, but I hope I gave you the picture of what I'm trying to do here to show you what we are trying. This work mainly was conducted by Joshua. He was working with me as an undergraduate student. He is a physics student, and then got his master's degree and started to work on this topic for his PhD degree, and just finished a couple of weeks ago. So now we can call him Dr. Guest. Okay, so with this, let's see. This is what we are going to try to work on. I'm going to give you an introduction, which actually I gave you the introduction without going through the slide. And then I'm going to show you why do we need X parameter, what kind of nonlinearity that we are expecting from those kind of elements. And then I'm going to go very quickly about finite difference time domain overview, only the parts that allow us to understand how we integrate some circuit element, whether they are linear or non-linear, into the finite difference time domain. And then how do we extract the X parameter from a finite difference time domain simulation? And then how do we basically use it and integrate it into another finite difference time domain as a black box, and then I'm going to conclude. I forgot to mention, please raise your hand at any point. Don't wait till the very end. If you have any questions, please ask me while I'm talking. That's how I would like to make presentations. So in terms of introduction, quick introduction, in addition to what I just mentioned, there are some active and nonlinear elements, and we would like to be able to handle them in a computational electromagnetic tool. Existing tools right now are basically, they solve the electromagnetic problem with one technique, and they solve the nonlinear component in another technique, and they do some sort of iteration between the two techniques. Our objective is to have only one electromagnetic simulator that handles all these elements. So it handles radiation, scattering, effective linearity, and so on. So this is basically our approach here in terms of creating a black box for the X parameter for nonlinear component. We focus on nonlinear component now because all other components that we have addressed before is already integrated in our finite difference time domain code. So where does the nonlinearity comes from? We have here a couple of examples. We use amplifier to increase the signal, oscillators to generate radio frequency, mixer, we use them to modulate and demodulate, and frequency multipliers, we also use them in many circuits. So all these different components are basically nonlinear, does have non-linear characteristic, and this non-linear characteristic we cannot represent it in an S parameter configuration, so we need to come up with something else, which is basically being called X parameter. So in terms of looking at circuits that has nonlinear components, there are different techniques, and if we look at all these techniques, obviously empirical one is approximation. The physical one has also some approximations. Experimental is very expensive, and obviously we can do this, but if the equipment are available and the resources are available. And then behavior model. And behavior model is basically to look at the device itself and see the behavior of the device for all kind of fundamental other frequencies, and extract something to be able to use it later on. And that's basically what we're going to do, to extract X parameter, put it in a black box, and put it in a finite difference time domain simulator. I mentioned to you that we already did something like this. If we have FET transistor here, that's the equivalent circuit. It does include a dependent source, and we managed to be able to put this entire configuration here into a finite difference time domain solver and get the output relative to the input, and we have seen the amplification. And this work, we have done it and published it about 13 years ago. So it's available. But as you see, it's very, very complicated, so many components, and between two nodes, for example, between these two nodes, I may be able to put a capacitor. I have to come to the next node to put a resistor. In here, I may have to break this into two nodes, one for resistor, one for inductor. So setting it up and working it out in a finite difference time domain simulation, it's going to be cumbersome a little bit, but we have to do it sometime if we don't have the X parameter simulation for the entire nonlinear device. So the X parameter, you can consider it as a superset of the S parameter, or the S parameter as a subset of the X parameter. X parameter is going to allow us to handle the harmonics, the cross-reference effects, and memory effects as well. Although I'm not going to touch on the last item here, but the first two items we're going to touch on them. We can measure it in the lab. The word easily here is basically a little bit exaggerated. It's not as easy as measuring the S parameter, but it's doable. The nice feature about X parameter, like S parameter, is that we can cascade multiple X parameter black boxes. So we can have one nonlinear device here, one nonlinear device here, and you can cascade them all together and come up with a combined black box for both of them. So let's look at this picture here. If I have a linear device here, I have an input signal that has a frequency and certain amplitude, the output is going to be another signal here. We notice that the frequency is the same, but the amplitude is different, and that's the effect of the linear device. In terms of frequency domain, you can see a frequency coming in, frequency coming out is the same frequency, but the amplitude is different. Now, if I change the linear device into nonlinear device, I have the input signal, the same input signal that I had before. I have an output here. Obviously, this has multiple frequencies. It's not only a sinusoidal waveform as the input signal. The amplitude is also different. If you look at the picture of the input and output in frequency domain, you can see one frequency coming in, and we have multiple frequencies with different amplitude coming out. So that's basically what we would like to know, how this nonlinear device, if we put it in an electromagnetic simulator, can we predict all these variations at all these frequencies or not? So the way to do it is basically to consider a wave coming into the nonlinear device, and we are going to call it the A wave. The A wave is going to produce a B wave coming out. This is a single frequency. This is the fundamental and all the harmonics of this frequency. And in addition to this, there will be some reflection towards the port number 1, and this reflection is also going to have some harmonic of the fundamental frequency. To label these things and continue to work with them, if this is the B wave, I'm going to have the two subscript. One subscript here represents the port, which is port number 2 here, and this K represents the harmonic, the fundamental and the harmonics. So this is an integer, represents the fundamental frequency and the harmonic. The same thing, we can see it in the A wave. I'm going to have the port described by the first subscript, and the second subscript L represents the fundamental. For example, A11, that's the A wave coming in port 1 with the fundamental frequency, and B13 is the reflected signal at reflected wave at port 1 with the third harmonic. So in addition to this, if I inject a small signal into the device itself, or if the conditions around the the device is going to generate an additional small signal, you are going to see that the output B wave is going to be incremented, or there will be an additional component added to it, and that's what we call it the small signal response. The previous slide showed you the large signal response, and this slide shows you the large signal response and the small signal response. So that complicates even the analysis of a nonlinear device and trying to present it in X parameter configuration. So this is how it is. The S parameter is very simple equation as you see it here. In the X parameter, when we talk about the B wave that is generated from an A wave hitting a nonlinear device, we are going to see one component here, and this component is going to be responsible for the large signal input, and this this summation here, double summation here, is going to be responsible for the small signal that is being triggered into the system itself. You can see here that X, FB here, and XS and XT, those are the X values that we would like to come up with and be able to extract it from measurement or from simulation to construct a black box and then use it later on. Again, the notation, as I mentioned, the first one represents the port, the second one represents the fundamental frequency or the harmonic. And let me explain the component of the X parameter representation of the output wave. The first, the operating condition of the nonlinear device is going to affect this term. And you can see the effect is here and here and here. And the phase of the input wave at port 1 is going to show up in these green symbols. And the small signal that we can inject into the system as well, or it can be generated due to the nonlinearity and the response of the system, is going to show up in these two, A and A conjugate. And the last basically formulation has 3 different parameters for the X parameter. These are 3 X's, one X is here, and one X is here, and one X is here. So these are the different parameters that affects the formulation itself and that affects the output wave coming out of the nonlinear device. Fortunately, we can group this term, and that's going to be responsible for the small signal term, and this would be responsible for the large signal term. When we started this research, we focused on the large signal term, and we did all the analysis and simulation, and then we extended this to the small signal term. So those who are here, who remember me here maybe 6 months ago, I talked a little bit about different topic, but I did mention X parameter. At that time, we didn't have any solution for the small signal term. Now we have it completely figured out. So the way it works is that for the large signal term, we excite the nonlinear device by an A wave, and no other RF signal should exist in the system. So no small signal should be around in order to be able to predict information about the large signal term. So this is basically how it will happen. Input wave, output wave, reflected wave, and now this B wave is represented, or the X parameter that represents this large signal is represented in terms of the B wave that we can get at the port B here, and that's basically the expression, and you can see a condition under it here. So the condition of the nonlinear device, biasing, temperature, all other conditions that affect the nonlinear device is going to affect the value of the X parameter that we can extract knowing B. If I know the B wave, I can create this term in the X parameter. Now, if I need to get the small signal response, then I have to trigger some signal into this nonlinear device. I'm assuming it is A22 here. And once I do this, the font of the computer is not the same as mine, so there are some approximation here. But in any way, you can see from this analysis, we should be able to get the two XS and XT that are representing the small signal expression or term of the X parameter. So the conditions could be input power, fundamental frequency, DC bias, and for large signal response, we don't have anything other than the main large signal that comes in to evaluate XFB, and then for a small signal, we need to inject a small tickle signal into the system to calculate XS and XT. Measurement-wise, this is one of the devices that measures the X parameter. It is specifically called BNAX, and sometimes it's called large signal network analyzer. And during the measurement, also, we really need to do some calibration for the S parameter, for the phase and the power, and that's why you see here a power meter as well is connected to the network analyzer. So now let's see how we interface the X parameter with the finite difference time domain. Assuming that we have the X parameter, let's assume we got it experimentally right now. How can I introduce it or interface it with the finite difference time domain? So a quick overview, finite difference time domain, if we have object like this, is going to be discretized in the computational domain, and you can look at different cuts and examine the configuration. Basically, we have nodes, cells, and every cell is characterized by a node, and the three edges that are connected to the node, this edge and this edge and this edge, they are going to have in their middle the electric field component, and the three faces that are connected at this node, they are going to have magnetic field component entering into the center of those faces. That's why you have HX, HY, HZ. So those 6 components of the electric and magnetic field are associated with this node IGK, and every cell in the domain has to be represented this way. Okay, so when we try to solve for this component, we basically update every component as a function of time, and the superscript n represents the time. For example, this is the new EZ in terms of the previous step EZ component multiplied by a coefficient, another coefficient times previous previously evaluated HY and previously evaluated HX. This is basically the updating equation of one of the 6 unknowns in finite difference time domain if we don't have anything other than scattering objects characterized by mu1 epsilon and sigma E and sigma M, which is electric and magnetic conductivity. In addition to this, you may need to add some sources in terms of voltage sources or instant plane wave and so on. And the solution is very simple, going over a time loop in which we update the magnetic field and the boundary condition, and then the electric field, and in between we can extract some values of the electric and magnetic field to calculate the voltage and current as well. We calculate the current from H field components, we calculate the voltage from the electric field component. So in this formulation, we can easily integrate all these parameters, and that was available in our book, for example, in the first edition 2009 and second edition 2015. Recently, we added the S parameter as a black box, and today I'm going to show you how we can extend this to have an X parameter as a black box. So the way to add all these components is basically to work with the J term that's basically added to an electric field, for example, if the component is along the Z direction. And this J term is basically the current density. We can relate it to the current. And we look at the IV characteristic across the 2 terminals of these components. The IV characteristic is going to be giving us the current in terms of the voltage. And the current, we can get the current density of it and insert it here. And that gives us the updating equation for any one of those components. Okay, now if I need to use kind of transistor like this, and if I use the equivalent circuit that I showed it to you before, it's going to be a little bit more complex and sometimes unpredictable because the transistor also does not work and become stable at all kind of input conditions. So that's a major issue also to look into it if you would like to integrate this into a finite difference time domain solver. However, if we would like to look at an arbitrary element, let's see here. So that's basically how we handle any element that's not characterized directly by E and H. So let me show you now how can I extract X parameter for a nonlinear system from a finite difference time domain simulation. There are 3 different types here of nonlinear system. Obviously, at that stage, I need to get the equivalent circuit of any one of those nonlinear elements integrated into the finite difference time domain and extract the X parameter. And the extraction of the X parameter is nothing more than coming up with the B wave. So the B wave that we have an expression for it that's already being describing the small signal and large signal input is the one that we would like to be able to extract it from the finite difference time domain simulation. No, something happened here. No. مش محتاج. Let's see if this will work. No? Okay. Okay. So we are at this point here to extract X parameter from finite difference time domain simulation. And here is, for example, one configuration that we